Our partner colligative property to the boiling point elevation is freezing point depression. And by depression, we mean getting lower, not like any kind of an emotional response here. So hopefully you don't have that emotional response here. So let's talk about what is necessary in order for something to freeze. When we go from a liquid into a solid, what's happening in our liquid phase is that we have these individual particles moving around. And then in the solid phase, they have all lined up and organized themselves into a regular repeating pattern, in most cases anyway, that is called a crystal. So each crystal has a specific shape. If you look at salt crystals with a microscope or with a magnifying glass, I guess you don't need a microscope for that, you can see that they are squarish. And they make these little cubes. Of course, you can make different shapes depending on how you dry, but salt, specifically table salt, NaCl, and its related compounds, these are all a cubic crystal structure because they make these little cubes. And it's at the microscopic level too. In fact, a lot of the physical characteristics of macroscopic things is affected by their microscopic characteristics. This isn't true for everything, of course, but we do see some parallels. So anyway, we don't need to learn about what kinds of crystal structures things have. What we need is just kind of this general sense that when we make a solid, then all of the particles are stacked together the way you would stack up a whole bunch of Lego bricks and make them into a solid wall, perhaps. So either that or, maybe stacking blocks, wooden blocks, if you prefer that as an analogy. So that means that when you stick these Lego blocks together, they are all stuck in one place, and you can't shift them from side to side, and they are all bonded to each other. And so the difference between that liquid and the solid is not just the particles, because the particles are exactly the same, right? If this is liquid water, this is solid water. Our molecules are exactly the same as they were before. 1 oxygen, 2 hydrogens, all bonded together. They don't change how they're attached in their individual atoms, just like they don't change how they're attached when you boil them. And when you melt them again, it's a reversible change and they go back to being liquid. What's different is that these particles are free to move and these particles are not free to move. So the liquid, our particles can move around, but the solid, our particles cannot. They are in fixed physical positions. So if we think about what has to happen for them to get into these fixed physical positions, just like adding a solute to our liquid water made it more difficult for us to boil because it was harder for the vapor pressure to form. The same thing is true for the solid, that with extra solutes that are in this solution, they interfere with crystal formation. They make it more difficult because they get in the way of our water molecules interacting with each other to get into that crystal form. And another way to think about this crystal forming is that when we reduce the temperature, think about what's happening from a kinetic molecular standpoint. We talked about this a little bit when we talked about gases. These particles are all bumping around, and the hotter the temperature, the more energy they have to bump around. As we lower the temperature, we reduce the energy of the particles. And so that's going to allow them to settle into these bonded locations in the crystal. So if our solutes are interfering with the crystal formation, that means we are going to have to reduce the temperature more to get those crystals to settle out. So that's why we say that the freezing point is depressed. It is lower when we add a solute. to a solvent. So let's take a look. Our calculations are exactly the same. So that's the good news, right? We have the same calculation as we just did for our boiling point elevation. We just have different numbers here. So our change in our freezing point, this is going to be calculated based on the molality and the freezing point depression constant. And the freezing point depression constant has the same kind of units that the boiling point elevation constant did. Let's go ahead and take a look at that table again from the book. All right, here's that table again. So before we just looked at the boiling points and the boiling point elevation constants. And here on the left, we have the freezing points and the freezing points constant. So our freezing points are still in degrees C. Our freezing point depression constants are in degrees C per molal. So take a quick look at these numbers for the freezing point depression constant. And now take another look at the boiling point elevation constants. Notice that in every single case, the freezing point depression constant is bigger than the boiling point elevation constant. And this is always going to be true. Our freezing point depression constants are always bigger than our boiling point elevation constants. So let's go ahead and try out our calculations with those same numbers that we worked with before. So we had a solution that was a sugar solution, and our sugar solution from the last video had a molality of 0.730 molal. It wasn't very concentrated. So if we calculate the freezing point depression for this sugar solution, 0.730 molal, and this time our freezing point depression constant is 1.86 degrees C per molal. So if you multiply that through, you get 1.36 degrees C. So this is how much the temperature will have changed. The main challenging thing with the freezing point depression constant is that you have to remember that we are subtracting this, excuse me, what did I just do here? It's using some weird, this is delta TF. All right, so we're subtracting the freezing point depression quantity, I don't need that number right here, from the freezing point of the pure solvent. So our new freezing point for water would be 0 degrees minus, and we'll give ourselves some decimal places there, 1.36 degrees C, or in other words, minus 1.36 degrees Celsius. So unlike the effect on the boiling point of the water, you might actually notice the effect of this sugar water solution on the crystallization of the water, because it's reducing it by a whole almost 1.5 degrees. So let's go ahead and take another practice look at both our boiling point elevation and freezing point, just for some extra practice doing calculations. So let's say that we dissolve 0.231 moles of a non-volatile substance into 1.26 kilograms, that would be a lot, of carbon tetrachloride. And we want to ask, what are its new boiling point and freezing point? Now, I want to make one little note here. When I wrote this problem here, I specified that we were dissolving this 0.231 moles of a non-volatile material. So I didn't specify what kind of non-volatile material it was, but the big reason why I said this was non-volatile is that it doesn't have a significant vapor pressure. And that's important because it would actually affect how our overall boiling point was going to look, and we don't need to worry about what the non-volatile material is doing. So that's why I put non-volatile. So if you see that in there, it's just to say don't worry about whatever that material it is. It's not affecting the rest of your outcomes, and all you need to worry about is our straight ahead colligative properties, that there's nothing complicated. So, all right, so let's review our steps. Our steps are going to be to calculate the molality, to then calculate the boiling point elevation and freezing point depression using the table, and then compare to the original boiling point and freezing point, also using the table. All right, so let's go ahead and do this. In fact, it would be a good idea if you just pause the video and do these pieces. Remember, this table is in our book, so go ahead and look it up. Okay, so welcome back. For the molality, you should have had a molality of 0.183 molal. That I put this together to make it super simple, so all you needed to do is divide the moles by the kilograms, and that was your answer. So for the boiling point elevation, I got 0.919 degrees C, and that's because our KB was equal to 5.02 degrees C per mole. So this would increase our boiling point by almost a degree. Our freezing point is much more significantly affected. I got almost 5.5 degrees. Excuse me. I'll keep 3 significant digits again. And that's because our freezing point depression constant is 29.8 degrees C per mole for carbon tetrachloride, so that one's pretty high. Okay, so our freezing point and our boiling point. The boiling point was originally 76.8 degrees C, and we are adding 0.919 degrees C, so keeping one significant digit, that gets us a new boiling point of 77.7, sorry, 1 decimal place. We're using addition rules, and so that means we need to maintain the smallest number of decimal places. So for the freezing point, our original freezing point is minus 22.3 degrees Celsius, and now we need to subtract 5.02 degrees Celsius, 5.45. So we still have 1 decimal place, and we're using addition-subtraction rules, so our final answer would be minus 27.8 degrees Celsius. So with this particular example, you would absolutely notice this effect to your freezing point, and you might notice the increase to your boiling point if you're using a high precision calculator or thermometer. Now, another factor that we need to consider when we're talking about these colligative properties is actually how many particles are actually dissolved. I've been avoiding this in my calculations by using things like sugar, which are non-electrolytes. But let's think about that for a second. We know that if we have sodium chloride and we dissolve it, then that aqueous solution is not like sodium chloride particles that are stuck together. it's really sodium ions and chloride ions. So if we had like a 1 molar solution, well, we'll make it molal just to stick with our units that we've been working at, right? So if we had 1.0 molal sodium chloride, we really have 1 molal sodium ions and 1 molal chloride ions because this splits apart, right? So that means that overall, we really have 2 molal stuff that's dissolved in the solution. And the colligative properties, they care about how much stuff is dissolved, how many particles are actually dissolved in the solution. They don't care about, like what our paper says. They actually care about how many particles are floating around in the solution. And so that means that when we do these calculations, we actually are going to add a factor. We're going to add the Van Hoff factor, which often gets abbreviated lowercase I, to the equation. And the equations that I'm talking about here are the boiling point elevation equation and the freezing point elevation or depression equation. So we're just going to add an I to this. And what this means is that when we do this calculation, we're going to multiply a Van Hoff factor to reflect how many particles have actually dissolved in the solution. So this is yet another reason why it's useful to know the solubility rules and the ions and their ion charges, so that way you can figure out whether something's going to be an electrolyte or not. So let's just look at what the Van Hoff factors would be for a few things to help you figure this out. So any strong electrolyte will have has a Van Hoff factor that is probably greater than 1. And generally speaking, we will approximate them as the number of ions that dissociate. So let's look at a couple of strong electrolytes and what the ions are, and therefore what the Van Hoff factor would be. So if we have something like hydrochloric acid, that's a strong acid, and so we know that it dissolves into H plus and chloride minus. And so our Van Hoff factor would be 2, because for each 1 HCl, we produce 2 ions. So if we look at something like calcium chloride, from our solubility rules, we know this is a soluble compound. And from the compound, we know that this makes calcium 2 plus ions and then 2 chloride ions. So that's 3 ions for each 1 CaCl2 that dissolves. Another strong acid would be H2SO4, and that would make 2 H pluses and 1 SO4 minus. So this would also have a Van Hoff factor of 3. If you do something like potassium chloride, that would be the same Van Hoff factor as the hydrochloric acid. It would be a Van Hoff factor of 2. So most of our ionic compounds, they're probably just going to be a 2 or 3, depending on what the chemical formula is for them. But please be mindful to really pay attention to what our compounds are, how many ions they make, and therefore what amplified effect they're going to have on the solubility, on the boiling point and the freezing point elevations. So let's look at a contrasting example here where now we're including the effect of having an ionic compound on our freezing point. So before, I had us dissolve sucrose, which is a pretty big molecule, and so a substantial amount of mass is going to not produce a whole lot of moles. So let's look at a similar kind of example, only this time we're going to use 32.4 grams of calcium chloride, and we're going to dissolve it in 150 grams of water. And let's calculate the new freezing point and the new boiling point while including these Van Hoff factors. So just as before, we need to calculate the molality, and we need to calculate our freezing point. So like if we go back up to our list here, here's our steps. Calculate the molality, calculate the boiling point elevation and freezing point depression quantities using our new equations, and then compare them to the originals. So let's go ahead and remind ourselves these are the equations that we're going to use. And the table is from the book. So go ahead and take a minute, pause the video, and go and do this calculation, and then we'll check our work. All right, so for step 1, I got 0.292 moles of calcium chloride. And so dividing by 0.1500 kilograms, I get a molality of 1.95 molal. So a much higher concentration this time. For my freezing point, I guess in my notes here, we'll just calculate the freezing point. We know that one's bigger, so we won't worry about the boiling point here. All right, so for our freezing point depression constant was 1.86 degrees C in water, or for water, and we had 1.95 molal. And because this is calcium chloride and it dissolves into 3 particles, our Van Hoff factor is going to be 3. So now this gets us 10.8 degrees C. So that means that our new freezing point is going to be minus 10.8 degrees C instead of 0. So you can see why this is going to be a really significant effect. And calcium chloride is actually used for ice melting, and it really has 2 parts. So calcium chloride, I think we mentioned this before, when it dissolves in water, it releases a lot of heat. And if you want to try this at home, you can go to the hardware store and pick up one of those ice melting bags. It's calcium chloride. And then just take some, throw it in some water. You can feel the increase in the temperature just by holding onto the outside of the container. And so not only is it exothermic, so it helps to melt the ice, but then it's going to also reduce the freezing point, so it's less likely to remelt unless, of course, it's really cold outside. And in that case, you might just need to add more calcium chloride to your solution. So in reality, our Van Hoff factors may not be exactly the same as the number of ions that are dissolved here. A lot of the time, it's somewhat less than this, but we're going to continue just pretending that these are doing ideal behavior, and we'll worry about complicating factors in later classes. So you should feel confident by now dealing with boiling point elevation, freezing point depression, and calculating the Van Hoff factors to make sure that you can realistically model how dissolving stuff into your solvent is going to affect the boiling point and the freezing point.